Here we are asked to calculate the entropy produced over the throttling valve. Our entropy balance tells us that it's equal to the change in state of entropy of the flowing streams. So, information given, we do not know this temperature. In addition, we are restricted by the path that we can use because we only know the Cp value at 500 kilopascals. If we apply our equation for the entropy change in state of the flowing streams, see we've got two unknowns in that equation, the entropy produced as well as the temperature at the outlet of that valve. Our energy balance provides us with a second equation that we can use to calculate that temperature at the outlet. If it was an ideal gas, remember, if there's no change in enthalpy, temperature in would be equal to temperature out. But now this whole equation means that there are two changes in the enthalpy, one due to a change in temperature, one due to a change in pressure. They must be equal but opposite in sign to result in the zero value for the change in enthalpy. The examiner was specifically interested to see whether you know which temperature to use in this equation and in the expression for the volume for this part of the change where the temperature is kept constant while we are changing the pressure. So the state of the gas is changed from its inlet temperature at 750 Kelvin to an unknown outlet temperature at 500 kilopascals. Since we only know the Cp value at 500 kilopascals, that restricts us to a very specific path when we analyze this change in enthalpy. In other words, this part of the change needs to take place at 500 kilopascals, meaning that we are forced to do this first, change the pressure to 500 kilopascals while we keep the temperature constant at 750 Kelvin. So this temperature is therefore the temperature that we must use when we evaluate the change in pressure. We can now calculate that unknown temperature out by applying our energy balance in the correct order of steps, and subsequently we can calculate delta S by remembering that now we are also restricted to that specific path. First, change the pressure while keeping the temperature constant at 750 Kelvin, and then calculate that change in temperature, with temperature out now a known variable. During this test, I recall that many students were too stressed to notice this temperature dependence of the parameter B. So when you do this problem, remember that you must substitute this whole equation as a function of temperature for B. So therefore, the resultant equation for the specific volume of that gas is a function of temperature that looks like this and pressure.